Hey guys, welcome back. Chapter 11. Yes, we only did several sections in chapter 8, so just the videos posted are the ones that you are responsible for. And we're just doing several sections in chapter 11. So here we go, our first section in chapter 11, titled Sequences in Series. In math, a sequence is just simply an ordered succession of numbers. So for example, I could have 1/2 maybe comes next, 1/3, 1/4, so that's my first, second, third number, fourth number, so forth and so on. What we do is we look for patterns in sequences. We often are interested in how sequences behave. If you had to guess the next term, you probably would guess 1/5, which is correct. And we could continue forever. Sometimes sequences are finite, meaning they just may have 6 terms like this. If you see the ... at the end, that means it continues this way forever. Each number in a sequence is called a term. So this is called the first term. That would be my second term, so forth and so on. This would be my 6th term. Formally, a sequence is a function whose domain is the set of natural numbers. Well, what does that mean? Well, it's a function because the first term, there's only one first term, there's only one second term, there's only one third term. So the input is the position it is in the sequence, and the output is the actual value. So for the example above, if we have the input, now the natural numbers are our counting numbers that start at 1. For the input 1, the output was 1. For the input 2, which is the second term of the sequence, the output was 1/2. For the input 3, the output was 1/3, so forth and so on. Output 4 was 1/4. And this, the way I indicated this sequence goes on forever. Now we tend to not use x though when we talk about sequences, our input variable. So I'm going to actually change this to n, meaning that we're inputting just the natural numbers. So I'm just going to stick with that notation. So n starts with 1, it's our natural counting numbers, and then it's the matching term in the sequence associated with that input. This actually has a formula. Not all sequences have formulas, but note, in this particular example, f of n is defined by 1/n. The first term is 1/1, the second term is 1/2, the third term is 1/3. So the nth term is 1/n. So if I wanted to know the 30th term of this sequence, I wouldn't have to write out all 30 of them. I could just do 30. I could just call it 1/30, so forth and so on. So this is actually a special type of template. It's called an explicit formula. An explicit formula defines each term of the sequence directly. So the nth term is found by taking 1/, the position it is in the sequence. This allows you to calculate any term in the sequence without knowing the value of the previous terms. So here's that formal definition. We like when we have explicit formulas. They define each term of the sequence directly. So the previous explicit formula was 1/n. The nth term was 1/, that position. So let's look at another example. I could say let f of n equal n minus 1/n. And if we made a table of values, we start with our counting numbers. At 1, we'd get 0/1, which is 0. At 2, we'd have 1/2, which is 1/2. At 3, we'd have 3 minus 1/3, which is 2/3. At 4, we'd have 3/4. 5, we'd have 4/5. So we can see that this sequence has this pattern: 0, 1/2, 2/3, 3/4, 4/5. So even without this template, we could probably see that the next term in the sequence would be 5/6, 6/7, so forth and so on. Now, when we have a sequence, we tend not to use function notation. So we're going to use sequence notation. Now, different books tend to do notation sometimes a little bit different. So what I'm going to say is the nth term of this sequence. So n is subscripts. Here it's our subscript. Its subscripts usually determine a position. So it's saying in the nth position, we have n minus 1 over n. So a1 would be 1 minus 1 over 1. And that's how we got 0. a2 would be 2 minus 1 all over 2. And that's how we got 1/2. So forth and so on. So to continue on with this notation, we often write our sequences like this. We use a curly bracket because this is a set of numbers, and the set of numbers is a sequence. We start in the first position, and then this was indicated with dot, 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 so it went on forever. It's an infinite sequence. But now to be more specific, I'm going to actually write the template for this particular sequence inside the brackets. There we go. So here is the sequence written as a function template, right up here. That is it written as the function template. Here's a table of values. Here we're writing it as our set, actually writing it out, and here we're just condensing it a little bit. We're using the bracket notation and then how each one is defined, each term is defined inside the brackets. So if I said, let's suppose I gave you this, let's suppose I had the sequence an, and we can get really crazy with this, to the n power times n squared. Okay, I might write this like this, -1 to the n times n squared. We typically start at n equals 1. You can start at any value. It's just standard to start at 1. If a sequence starts anywhere other than 1, maybe at 0 or 2 or 3 or 4, it would indicate it here. And then if it's an infinite sequence, we'll put infinity up here. We can just do a finite sequence. Maybe we only want to see the first 5 terms of this sequence, so we would put 5 here. But I like infinity. So this would look like, well, if n was 1, -1 to the n power is -1 times 1 squared would be -1. If n was 2, -1 squared is +1 times 4. If n was 3, we'd get -1 cubed, which would be -1 times 9. And maybe you're seeing the pattern. At 4, we're going to have 16, but this will be positive, so we'll have +16. So this isn't what we call an alternating sequence. The terms are alternating between positive and negative, and that's being forced by this part of the template right there. And then every number is just that position squared. So 25, if n was 5, this would be 25, but then that would be -1, so it would be -25, 36, so forth and so on. So those are some examples of some explicit formulas. Note, if I did this, perhaps I just said we wanted to look at the finite sequence, -1 to the n times n squared, n equals 1 to 5, for example, then this would just be -1, 4, -9, 16, -25, and we would stop there. So if this is a finite value here, you only write out up to that term. If it's infinity, obviously we can't write these numbers forever, so you would indicate that with the dot, dot, dot. All right, now unfortunately, not all sequences have explicit formulas that help you find any number. So like for this example, also note, if I wanted to find the 100th term, so A with a subscript 100 tells me if I was to list these out, I don't have to list the first 99 terms to find the 100th term, because this template tells me the 100th term is going to be -1 to the 100th power times 100 squared, which would be, well, this is an even power, so that's just going to be +1, and 100 squared is 10,000. So if I was to write this out, I know the 100th term would be 10,000. So we could do that for any term in this sequence. Unfortunately, not all sequences have explicit formulas. Some have no formulas, but some have a different type of formula called a recursive formula. A recursive formula defines each term of the sequence using preceding terms. So what comes next is decided by the previous term. So for example, we could do, this is one of the most famous recursive sequences. I'm going to start with 1. The first term is 1. The second term is 1. The third term is 2. The fourth term is 3. Do you know what the fifth term is? 5. 1, 2, 3, 4, 5. The sixth term is 8. And yes, there's a pattern here. I'm not sure if you see it yet. 13. 21. All right, so how did we get 1 to 1 to 2 to 3 to 5? Right, well, the trick here is this is called Fibonacci's sequence. And Fibonacci sequence has really cool history. If you're bored in your time at home, feel free to Google Fibonacci sequence. All these numbers in this sequence are called Fibonacci's number. So if we were to keep going, 34 is Fibonacci's number, and then 55 is a Fibonacci number. Any number in Fibonacci sequence is called a Fibonacci number. And we start with the third term, and the third term is obtained by adding the previous two terms. So we get 2 by adding 1 and 1. Well, we could do that here. We can start with 1, and it's added by the previous two terms, and there's nothing here, so 1 is 1 plus nothing, and it's 1. Add those two, we get 2. Add number 2 and 3 to get 4. Add 3 and 4 to get the fifth term. Add the fourth and the fifth to get the sixth term, so forth and so on. So 13 is obtained by adding 5 and 8. Now, for years, mathematicians have been trying to find an explicit formula. If we wanted to know, say, for example, the 100th term or the 10,000th term of this sequence, we'd actually have to list every one preceding it. But we can describe how the sequence behaves. We just can't describe it explicitly. I can't find a template for the nth term. But we have what we call a recursive formula. The recursive formula for this would be, well, the nth term is the sum of the two terms before it. So how we write that out mathematically? Well, the term before the nth term is the n minus 1 term. And then the term 2 terms before this term is the n minus 2 term. So for example, the 7th term, this is telling me that the 7th term would be the 6th term plus the 5th term. So if n is 7, this would be 7 minus 1, and this would be 7 minus 2. So this is the template for the Fibonacci sequence formula. And again, it is recursive. It's telling me how the terms of the sequence are behaving, but it's not allowing me to find a term way down the list. If I wanted to find the 100th term, I would need to know the 99th term and the 98th term. So in order to know the 99th term, I'd need to know the 98th and 97th. So I'd have no choice to find the 100th term. I'd have to list the first 99 terms to find it. So that is a recursive formula. A little blurb on factorials. You may or may not have seen these in your math career. An exclamation point has meaning mathematically. Like I said, you may or may not have seen this before. A factorial only works if it's placed after a positive integer, or no, I should say that a non-negative integer. So you have to start with a non-negative integer, and 5 factorial, whatever this integer is, you take that number and you multiply it times all the integers that fall below it. I'm sorry, all the non-negative integers that fall below it. So 5 factorial means 5 times 4 times 3 times 2 times 1. So that's 120. So, I don't know, let's see if I said find 10 factorial. Well, that would be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And you can imagine that would be tedious even to put in your calculator. But if you have one of these handy dandy graphing calculators, if you go to the math button, 3 buttons down on the, actually put in the 10 first, and then go down 3 buttons down on the left. I have a math button, and I go 3 over to PRB. And the fourth thing down is exclamation point. I hit that, and it's 10 factorial, and I hit enter, and it tells me that it is 3,628,800. So you don't need to have a graphing calculator to find that. If you can can see that there. But it's not a bad tool to be able to find. We like factorials. They often appear in sequences and series. So it's not a bad idea to get familiar with them. So let's just take a couple notes here. Think simplifying. Let's suppose I said something like, you have a 10 factorial over 8 factorial. There's no need to do both of these in your calculator. Thinking in mind, this is 10 times 9 times 8 times 7 all the way down. And this is 8 times 7 times 6 all the way down. But if you notice, the factors from 8 down cancel. So 10 factorial over 8 factorial is just 10 times 9 because from 8 down cancels and it's just 90. So keep that in mind when you're simplifying factorials. If it asks you to do stuff like that, just cool little tricks. Also note, 1 factorial is just 1. It's just itself. But this is the weird one, 0 factorial. We use factorials a lot when we do permutations and combinations and probability. 0 factorial is also 1. So if you don't buy it, maybe you'll trust your calculator. I'm going to hit 0 in my calculator. And I'm going to go to math, over to PRB, go down to number 4, and I hit enter. And 0 factorial, there you got it, it's 1. Yep, so 1 factorial, math, PRB. 1 factorial is also 1. All right, so 0 factorial is 1. That's a fact. 1 factorial is also 1. Just a cool bit for those of you that might be interested on why 0 factorial is 1. Let me show you algebraically. Well, notice 6 factorial is right, 6 times 5 times 4 times 3 times 2 times 1, right? So 6 factorial divided by 6 would be this, and these would cancel out. So 6 factorial divided by 6 is just 5 factorial. So that being said, 9 factorial divided by 9 is just 8 factorial. 100 factorial divided by 100 is just 99 factorial. So in general, z factorial divided by z is z minus 1 factorial. Right, let's do it. Let z equal 1. 1 factorial over 1 is 1 minus 1 factorial. This is 1 equals 0 factorial. Okay, so just a little cool blurb of information. All right, now that we have a brief introduction to what a sequence is, let's talk about what a series is. Given a sequence, finite or infinite, whoops, there goes Siri again. Given a sequence, finite or infinite, the sum of the terms of the sequence is called a series. So given A1, A2, A3, A4 forever, this is a sequence, then the corresponding series is just the sum of these terms. Right, notation. A1 plus A2 plus A3 plus A4 forever. In math, when you see the Greek letter sigma, sigma means sum in math. So this says sum up. And we use generically a subscript of I. So this says sum up all the A's with the subscripts. And we're going to start with 1. So I is going to go from 1. Now this, what goes up here depends on where we're going to stop. This is not stopping. This is an infinite sequence that I presented you with. So it corresponds to an infinite series. So we add up the first n terms Oh, if we add up all the terms of an infinite sequence, we get what we call an infinite series. Just an alternate form on the notation. We can also write this as, sometimes instead of using i's, they use n's. All right, so that doesn't change things. This just says start with n equals 1 right here, and it's assumed that we're increasing in increments of integer values. So if we have a finite sequence, the corresponding sum is called a finite series. So if we just have n terms, so maybe up to 10 or 20 or 30, so a1 plus a2 plus a3 plus, but we're going to stop at the nth term. We could call this the kth term, the wth term. All right, now here we're going to start with, we tend to use the subscript I because n is here representing the very last term of this sequence. So we would write, if we're writing up the first n terms, we would write it starting at 1 and ending at n. Consider, let's do 1 over n equals 1 to 5, which corresponds to 1, 1/2, 1/3, 1/4, 1/5. So the corresponding series for this finite sequence, I'm trying to be consistent with my notation. I'm going to let I equals 1 to 5. So this says first plug in I equals 1, so it's 1 over 1, plus, and then go all the way up to 5 in increments of integers, plus 1/2, plus 1/3, plus 1/4, plus 1/5. And we could add that up, whatever that happens to be, and that has a sum. Or we could use this notation, 1 over n, because we know the specific value we're starting with. We're going to say we're going to start at 1 and end at 5. We get the same result. So don't let the swap between n's and i's change things. So whatever that value is, let's just for kicks, we're going to do 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. And this has a value of a nice 137, 1/2, 1/3, 1/4, 1/5, 137 over 60. Now, if you do this in decimal form, it's like 2.283333333. That's not going to be an exact value and probably not asked for in ALEX, so make sure that you follow the directions, and if it asks for an exact value, you convert it back to your fraction. All right. So if we have a finite sequence and we add up a finite number of terms, it's called a finite series. If we have an infinite sequence, the corresponding sum is called an infinite series. So, a1 plus a2 plus a3 plus forever, we would write I equals 1 to infinity, or you can write an, and the subscripts are varying from 1 to infinity. So for example, let's suppose I had 1 over n squared. And n is going to start with 1, n equals 1 to infinity. All right, so this is going to be 1, 1/4, 3, 1/9, 1/16 forever. So therefore, the infinite series would be 1 over I equals 1 to infinity, or we could write it as n equals 1 to infinity, 1 over, n I squared, n squared. In either case, we would get 1 plus 1/4 plus 1/9 plus 1/16. cool fact, something cool. If I add, let's go back to these guys. Like if I added this up forever, I'll get back to that in a minute now. Take that back pedal, something cool. Consider the series n equals 1 to infinity, 1 over 2 to the n, which equals 1/2 plus 1/4 plus, if I put 3 in there, 2 cubed is 8 plus 1/16, right? Now it might be your thought that if we add up an infinite collection of numbers that this sum must be infinity, right? Because we're just keep adding and adding and adding. It's not true. As a matter of fact, if we add this up, it equals 1. If we add 1/2 plus 1/4 plus 1/8 plus 1/16, it just equals 1. But n equals 1 to infinity, 1 over n, which is 1 plus 1/2 plus 1/3 plus 1/4. If we add that up, it does go to infinity. So cool things that we talk about, if you get up to Calc 2, we talk about how series behaves and what can make a series actually equal a finite value. If we add up this infinite collection of numbers here, coming from the sequence 1 over n, and you keep adding 1/2 to 1 and then add 1/3 to that sum, then 1/4 to that sum, this sum will grow without bound, but this sum will never exceed 1. And if you sat there with your calculator and did this forever, I promise you it would be 1. So cool fact. All right, so some not fun stuff. Properties of summation. I don't like writing this stuff down, but I'll do it anyway. Let's see. Properties of summation, just to end this section. Properties of summation. The first property is, all right, so this is actually good for a notation thing. All right, so if we're just adding a constant, notice there's no sequence notation here. There's no I, nothing is changing. This is just going to be C times N. What does that mean? It says that this C just represents the constant series. So let's suppose we had this series, 3, 3, 3, 3, 3, kind of boring, but it is still a sequence, which then would correspond to the series 3 plus 3 plus 3 plus 3 plus 3 forever. So therefore, the corresponding series for this sequence would be n equals 1 to infinity of just 3. So that's how we would write that. This just means 3 plus 3 plus 3 an infinite number of times. Now you can imagine that is, as if we kept adding 3 an infinite number of times, that will equal infinity. But this little template is saying, well, let's just suppose we add a finite number of 3's, like 1 to 4 3's. This just means 3 plus 3 plus 3 plus 3, which is just 4 times 3. And that's what this little template is saying. It's how many times you're adding it together, just multiply it by that constant. So I don't think it's a super useful template, but it's in your book, so I'm including it. All right, second property says if you have a constant times the terms of the sequence and then you add that up, it says that you can pull this out and maybe it will make the math better. Let's see, make the math easier. I'm going to go back to this guy. So for example, let's suppose I had 3 times 1 over n. So if I looked at this from n equals 1 to 5, this would be 3 over 1 plus 3 over 2 plus 3 over 3 plus 3 over 4 plus 3 over 5. So therefore, the corresponding series would be n equals 1 to 5. 3 times 1 over n. Now notice these all share a common factor of 3, so we can pull the 3 out, which means in summation notation, we can pull it out in front of the sum. And why would that be helpful? Well, if I pull all of these threes out, I would have 3 times 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, which would be this sum, which we just calculated to be 3 times 137 over 60, which would be 137 over 20, 3 and 60. So we just found that summation with minimal work. If you have multiple terms in a series, let's suppose we had, well, let me write the template down. So if we had multiple terms in a series in adding or subtracting, and this doesn't matter if it goes up to n or goes up to infinity, we can split this up. And we can just look at this first part, and then we can add or subtract going along with whatever that sign is. Like this. And this could be, this works for both infinite and finite series, so I could just go up to n, or I could go up to infinity. So for example, this property says, suppose we're studying, let's suppose we had 1 over n, n equals 1 to infinity plus 3n. It says we could look at this and study as 2 separate entities, n equals 1 to infinity, 1 over n, plus, and then we could look at it, n equals 1 to infinity, 3n. So we could study them separately if necessary. All right, so what I'm gonna have you do is, uh-oh, I wrote it down, give me a second. To do read 11.1 exercises 7 to 79. I don't know, every other odd maybe. I mean, you can do every odd. The more problems you do, the better you will get at them. So I suggest doing as many problems as possible. And for your Alex percent, you can now work on Alex 11.1 topics. See Blackboard for this week's percent. Because I forgot to write it down. Anyway, hope everybody's well. Don't forget to zoom in if you have questions or concerns. Looking for some company. Take care, guys.